Okay, so let's do where we're supposed to be at is calculus. So we're going to start intro to calculus. And so I put together this PowerPoint presentation. So what I'd like you to do first is I want you to, so let's take a look at this presentation. Let's see if I got it. Perfect. Intro to calculus. And then the introduction, what I'd like you to do is I want you to go to Desmos and I want you to enter this in. So pause the video and I want you to enter this all in. And then what I want you to do is I want you to go through this PowerPoint presentation. So what I'm going to do is I'm going to just show you the slides right now. So let's see. So I asked you to do this. You pause. Then you come back. The tangent line. You should see a curve f of x, y. I want you to tell me what's going on with the line. What's the equation of the line from the Desmos code, and why it doesn't look like y equals mx plus b. I want you to explain the parts of the line, and then I want you to explain what represents the slope. I mean, every line has to have a slope in there. What part of the code represents the slope? So once again, you're going to pause, so you're going to answer this question. Okay, so let's go back. So once you've paused it, you've done it. So let's go to Desmos. Whoops. So let's get out of this and let's go to Desmos. Here we go. And here it is. So we put the code in, and so we have g of x equals this funny symbol d over dx f of x. A is 3. Then we have this equation. You can see that the blue line is the cubic, and the red line is this line. That's our tangent line. And when I put the slider on, and as a moves across from -10 to +10, let me slow this down a little bit. We can see it's like, the way I describe it, it's like a surfboard. It's like surfing along the curve. And we're really interested in this line. This is the tangent line. And what we're also interested in is in the slope of the tangent line. That's the slope of the tangent line at each point. That's known as the derivative of the function at the specific values. And that's what we're focusing on. So you can see it. And so the question is, what is, so the next thing I asked was, how is this line represented? Right? Is it in there? Oh, let me go back. Sorry. Let's go back. Sorry. So where was the PowerPoint? Yeah, so d dx represent what we will be studying, the derivative. We are going to manipulate the original function and substitute specific x values, the slider a. This will give us the slope of the tangent line. We will eventually see the slope of the tangent line will represent the rate of change at a specific point. It's like the slope of the line, but now it changes. So the tangent line. So I'm sorry, let's go back to Desmos for a second. So the next question I asked was exactly what, let's see if I have, here's my line. Wait, do I have the thing down here? Highlight, eclipse, eraser, nah. Up. So right here. So the question is, what is this? The equation? Where's what's going on here? Well, what is this equation? And what I want to get to, it's point slope, right? So it's y minus y1 equals the slope times x minus x1, or the xy value. And you can see here, we have the point f of a, and we have x minus a. This g of a, that's the slope. This thing called the derivative is the slope of the line. We're going to make those connections a little bit later, but once again, this is just an introduction. So let's go back to the tangent line. So what we're interested in is this relationship between that tangent line, the line, and the curve. Is there a connection between the slope of the line and the curve? And the answer is yes. So in the rational functions unit, we were concerned with whether when the function was increasing, decreasing, or neither. Do you think the slope of the tangent line is connected to the behavior of the function? What are the possibilities? And so, what do you think? So let's go back to Desmos, and let's bring our slider back right here. So let's reverse and let's slow it. Come on. Let's speed it up. Sorry. Let's speed this up. Sorry. I want to slow it down. Okay, so the question is what's going on now? We can see the slope is increasing. The function is increasing. No, sorry. I apologize. Okay, right now, the blue graph, we're moving from left to right. The blue graph is increasing. What's the slope of the tangent line? It's positive. Then what happens? What's going on here? Right there. Is the function is neither increasing or decreasing, the slope is zero. What happened? Then the function is decreasing. What is the slope of the tangent line? It's negative. It's decreasing, the slope is negative. It's decreasing, the slope is negative. Let's pause it right here. Let's move it. What's going on there? We have a turning point. The function is neither increasing nor decreasing, and that corresponds to zero slope. Now the function is increasing, and that corresponds to a tangent line that has a positive slope. That's the connection. Sorry for that. I'm trying to make this. So, do you think the slope of the tangent line is connected to the behavior of the function? What are the possibilities? We'll write this down in a second, but the connection is, as the function is increasing, the slope of the tangent line is positive. When the function is decreasing, the slope of the tangent line is negative, and when there's a turning point, when it's neither increasing nor decreasing, the slope of the tangent line is zero. There's going to be an exception in higher level math. For example, think about the curve y equals x to the third. Right? Let me change that actually, because I told you can change it. I'm going to change this. Let's get rid of this for a second. What's going on here? So, right, it's increasing, and then it's increasing, but what's the slope approaching? It's approaching zero. Then that necessarily does not mean a change in direction. This is a rare exception. It might show up in higher level. It's called a saddle point. We're not really going to talk about it. But in general, when there's a turning point, that's when the slope is zero. Let's move on. Now, the exercises in the book ask you to sketch the derivative based on the function, and they ask you to sketch the function based on the derivatives. So let's take a look at that. So we're going to go to, there we go. Question number 1, sketch the derivative, sketch the derivative of this function. So the first thing I'm going to do is I'm going to put in the surfboards, right? Surfboard, 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 surfboard. These are tangent lines. So I look here and I say, I'm going to write this down. I'm going to write F, and I'm going to write F prime, right? Let's call this So let's break this up. This is A, and this is B, right? So from negative infinity to A, my function is increasing. At A, I have a turning point. From A to B, my function is decreasing. At B, I have a turning point. And from B to infinity, my function is increasing. Well, what does that say about the surfboard? Well, if the function is increasing, the function is positive or above a positive, the derivative is positive. At the turning point, what did we say the slope was? 0. When the function was decreasing, we said the derivative, the slope of the derivative was negative. At the turning point, once again, when there was a turning point, the slope is 0. And when the function is increasing, we said the derivative is positive. Let me change the color. No. Let me change the color to blue, right? Now let's sketch the derivative. Well, we said here it was positive, and then it reached 0, right? It was positive, then it reached 0. When the function was decreasing, so let's see, positive, 0. Now from A to B, the function is decreasing, therefore the derivative is negative, right? What happens at B? It goes back to 0, and then from B to infinity, because the function is increasing, the derivative has positive values. Let's move on. Once again, pause the, slow me down, pause the video to take a look at the picture. We're going to move on to the other one. Sketch the derivative. Sketch the derivative of this function. Same idea. So let's see. I want to go back to red. But you know what? I'm going to do blue. No, I'll do. Hold on a second. Let's see. Oh, that was a. Let's see. Sorry. Okay. Oh, come on. You can speed this up. Sorry. Okay. So we'll stick with the blue. I'm going to sneeze. Sorry, a sneeze is coming on. So let's sketch a derivative of the function. This is the function in front of us. So we're interested in. Let's once again. This isn't what I wanted to do. Hold on one second. I'm sorry. I wanted to go let's do it. You know what? Oh, it's the same exact thing. I apologize. Wait, so the other thing is somewhere. You know what? I'm sorry. I apologize. Okay. Hold on one second. Just put it on pause. Or speed. All right, let me go back to the book. Let me go to the book. This is what I want to do. Sorry. Okay, so this one is, sorry about that. I want to do this. Let me see. You're given the derivative. Find a sketch of the original function. Sorry about that. Okay, let me set this down. I apologize. No. Sorry. Perfect. Okay. Good. Sorry, I apologize. Sorry. You're given the derivative of a function. Sketch the graph of the original function. Okay, let's take a look at this. So Let me get back on the thing. So I'm looking at this function. This is the derivative. This is the derivative. So this is negatives and positives. So I'm going to make a chart. I don't know f, but I do know f prime. F prime is another way of writing the derivative. Sorry. So what's going on here? This is A. This is B. And this is C. What's going on between A, from infinity to A? Let's see, A, B, C. From negative infinity to A, the derivative is negative, which means the function is going to be decreasing. What's going on at A? A is 0, which means this is going to be a turning point. So let's say this is decreasing, then a turning point. From A to B, the function, this derivative is positive. It's above the x-axis. It has positive values, which means the original function was increasing. Once again, b is 0. That means there was a turning point. What's going on between b and c? The curve is below the x-axis, so it's negative. Therefore, the function is decreasing. At c, it's 0, which means the function has a turning point, and from c to infinity, it's above the x-axis, which means the function is increasing. Let me change my color. What color should I choose? Okay, purple. No, let's make it yellow. Nope, let's undo that. No, you know what? Let's leave it yellow. Let's change the color. Display, color, perfect. We're going to make that, we'll make that blue. Okay, so let's see. From the function was decreasing, turning point, increasing. At B, there's a turning point. Decreasing. At C, there's a turning point. And it's increasing again. A couple of things. I really don't know if it's this high up or if it's this low down. Also, I don't know that the turning point of A and C are the same. I just know right now, the first day of calculus, there's a turning point at A and C and B, and that it's decreasing, increasing, decreasing, increasing. That's it. That's all I know. The last thing I want to talk about is sketch the derivatives of the following showing intercept with the x-axis. Let's just bring like lines together with let me get rid of that. Sorry. Let me get rid of this. Okay. Now sketch the derivative. Well, the derivative is it's those surfboards. And you're like, wait a minute. Surfboard, 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 surfboard. The surfboard is the slope of the line. The derivative is the slopes of the surfboard. The slope of the slopes of all those surfboards is the slope of the line, and it's constant, right? So what's the derivative? It's always positive, but it's not changing. It's actually fixed at 3. So this is the derivative. What's going on here? At the second example, same idea. Surfboard, surfboard, surfboard. The slopes of the surfboards are always, what is it? It's 1 to the right, down 1/2. So the slope is negative 1/2. It's always the tangent line, the derivative is always negative 1/2. Every single surfboard always has a slope of negative 1/2. And the last thing I want to talk about is something really interesting, that the function for the first one right here, it was a cubic, and the derivative, what was the derivative? Do we draw on the derivative? Or I erased it. What was the derivative? Let's see. The derivative was positive, negative, positive. The function was a cubic. The derivative was a quadratic. What's going here? What's going on over here? What was the derivative? The derivative was the derivative was the derivative. The derivative was a cubic, and the function was a quadrat. The derivative was a cubic, and the original function was a quartic. Coincidence? I don't think so. We're going to see that's the rule for finding derivatives. Of polynomials, you lower the exponent by 1. What's going on here? This is the function was y equals mx plus b. The derivative, 1 to the first, the derivative is just a slope. Same idea here. The function is the line, right? And the derivative is just the slope. Not a coincidence. That's the end of the video. Take a look at 16a and see what you can do.